Evolution doesn't have a plan. That's the part most people intellectually accept, but rarely sit with long enough to understand what it actually means. There's no engineer running calculations, no designer checking structural tolerances before committing to a body plan. Natural selection works entirely in hindsight. It rewards what survived yesterday, with no way to anticipate what tomorrow's environment will demand. And occasionally, that blind process builds something that works magnificently, scales it up across millions of years, and then discovers, too late, that it has constructed something the physical world cannot permanently support. This is a story about what happens at that moment. Not the extinction itself, but the architecture of the mistake. The concept at the center of this is called Cope's rule, named after the 19th century paleontologist Edward Drinker Cope, who observed a consistent pattern across the fossil record. Animal lineages tend to increase in body size over evolutionary time. The reasons are logical. Larger animals are generally better at competing for resources, more resistant to predation, more capable of thermoregulation, and more efficient at certain types of locomotion. Size confers advantages that are immediate and measurable. What Cope's rule doesn't account for is the other side of the ledger, the compounding costs that accumulate as size increases, costs that only become fatal when the environment stops subsidizing them. To understand where those costs become catastrophic, you need a specific example that illustrates the failure mode rather than just the pattern. Paraceratherium, formerly known as Indricotherium, is that example. It was a hornless rhinoceros relative that lived across Central Asia between roughly 34 and 23 million years ago, during the Oligocene epoch. Conservative estimates place its shoulder height at around 4.8 meters, and its mass between 15 and 20 tons. Some specimens suggest individuals approaching 25 tons. It was the largest land mammal ever confirmed to have existed, and it got there through a straightforward application of Cope's rule in an environment that, for a long time, rewarded every step of the journey. The Oligocene landscape that Paraceratherium inhabited was dominated by open woodland and scrubland across the vast Asian interior. The animal's extraordinary height gave it access to vegetation in the upper canopy that no competitor could reach. Its size made it essentially predator-proof for most of its adult life. The food source was abundant, the competition was minimal at its specific feeding height, and the body plan was mechanically sound. Large pillar-like legs, a relatively short neck that still reached heights no other browsing mammal could access, and a digestive system capable of processing enormous quantities of low-nutrition vegetation. On every metric available at the time, Paraceratherium was a success story. The problem arrived gradually, the way the most dangerous problems usually do. The Oligocene transitioned into the Miocene, and with it came a global cooling and drying trend that restructured vegetation across Central Asia. The open woodlands that had sustained Paraceratherium's feeding strategy began contracting. Forests fragmented. The high canopy vegetation that had been the animal's exclusive resource became patchy and unreliable across the vast distances a 20-ton animal needed to cover to sustain itself. And here is where the size that had been an advantage reversed its polarity entirely. A 20-ton animal cannot survive on the food supply that sustains a 2-ton animal. The caloric mathematics are unforgiving. Paraceratherium needed to consume somewhere in the range of several hundred kilograms of vegetation daily just to maintain basic metabolic function. When food sources became fragmented across an increasingly arid landscape, the animal couldn't simply reduce its intake and wait for better conditions. Its size had locked it into a minimum caloric threshold that the environment could no longer reliably meet. It wasn't hunted to extinction. It wasn't outcompeted by a faster or smarter rival. It starved at scale, across a continent, over thousands of generations, as the world it had been built for slowly became a world it couldn't feed in. This is the mechanism that Cope's rule consistently fails to predict. Size increases happen in environments that reward them, but those environments are never permanent. The fossil record shows this pattern repeating with enough regularity that it constitutes something close to a law of its own. Call it the ceiling problem. Every lineage that follows the size increase trajectory eventually encounters a ceiling, and the animals nearest that ceiling when the environment shifts are the most vulnerable precisely because they have the least flexibility. A smaller relative of Paraceratherium could reduce its range, shift its diet, find a microhabitat. A 20-ton animal has nowhere to scale down to. Evolution rewards the edge until the edge becomes the exposure. What makes Paraceratherium's story particularly instructive is that it wasn't a biological failure in any absolute sense. The animal was exquisitely adapted to its environment. Its bone structure was optimized for load-bearing at a scale that required specific architectural solutions. Wide, flared feet to distribute weight, dense leg bones that functioned more like structural columns than the limbs of a running animal, a cardiovascular system capable of supplying blood to a body the size of a small building. It worked. It worked for millions of years, across a geographic range spanning from China to the Balkans. The failure wasn't in the design. The failure was in the assumption, built into the design through millions of years of selection, that the environment would remain stable. There are genuine uncertainties still surrounding Paraceratherium's extinction. The exact timeline varies by region. Populations in different parts of Asia appear to have declined at different rates as the Miocene climate changes progressed unevenly across the continent. Whether there was direct competition pressure from other large herbivores moving into its range as forests fragmented is debated among paleontologists. The fossil record is extensive enough to establish the broad picture, but not yet detailed enough to reconstruct the collapse region by region with full confidence. What isn't debated is the pattern. Paraceratherium joins a list that includes Megalodon, Arthropleura, the giant ground sloths of the Pleistocene, and the enormous sauropod dinosaurs of the Jurassic. Animals that reached the upper boundary of what their environment and biology could jointly sustain, and then discovered that the boundary was a cliff edge rather than a plateau. Each of them got there through a process that was entirely rational at every individual step. Each selection pressure that drove the size increase was real and valid in its moment. The problem was never any single step. The problem was the destination those steps were building toward without any mechanism to recognize it. There's a broader principle here that extends well beyond paleontology. Any system, biological, economic, institutional, that optimizes relentlessly for a single variable in a stable environment builds fragility into itself proportional to how successful that optimization becomes. Paraceratherium was the most optimized large herbivore on Earth for its time and place. That optimization is precisely what made it irreplaceable in its world and irreplaceable in its extinction. There was no fallback. There was no smaller version waiting in the wings. When the world changed, the thing built to fit it perfectly had no room left to adapt. Evolution tried to build something too large. For millions of years, it succeeded. Then the definition of too large quietly shifted, and the most successful animal on the continent became, almost overnight in geological terms, an animal the world could no longer afford to keep alive. The lesson isn't that size is a mistake. The lesson is that optimization without flexibility is always, eventually, a form of vulnerability. And the more successful the optimization, the less visible that vulnerability is until it's too late to matter.